Have you ever wondered what it would mean if I told you that some particles might actually move against time itself? Not just that they have the opposite electric charge, but that they literally seem to travel toward the past. It sounds like science fiction, but it isn't. This idea comes straight from modern physics, supported by both mathematics and experiments. Today, we're exploring a strange and fascinating question. Does antimatter really move backward in time? And if even part of that idea is true, then how much about time, the universe, and reality have we been misunderstanding? Okay, in school, we're taught something simple. The electron has a negative charge, and the positron is its opposite, the antimatter version with a positive charge. That explanation is correct, but it's only the surface. What most people never hear is that when physicists do deep calculations, they don't always treat a positron as just a separate kind of particle. Instead, the math works better if you treat it as though it were an electron traveling backward through time. At first, that sounds like nothing more than a clever trick, like imaginary numbers that help in equations even though you never see them in real life. But here's the catch. If physicists don't treat positrons that way, their equations fail, predictions go wrong, experiments won't match. And when they do use the backward in-time electron interpretation, suddenly everything lines up with incredible accuracy, sometimes to 11 decimal places. In science, precision like that is almost never a coincidence. To visualize interactions, physicists use something called Feynman diagrams. In these diagrams, time is drawn going upward while space stretches sideways. An electron is shown as a simple line moving forward, while photons, particles of light, are drawn as little wavy lines. But when a positron appears, something unusual happens. Its line looks like it's going downward, as if it's moving the opposite direction in time. When an electron and positron meet, they annihilate and become photons. If you mentally play the diagram, it looks as though an electron emits a photon, turns around, and heads back the way it came, and that reversed segment is exactly what we call a positron. This naturally raises a big question. Is this just mathematical poetry, or is it genuinely how reality behaves? Physics doesn't usually answer with philosophy. It builds models, tests them, and keeps the ones that match experiments again and again. Right now, the models say that interpreting antiparticles as particles moving backward in time is not only convenient, it works astonishingly well. And when something works that well in science, we don't ignore it, even if it sounds unbelievable. There's an even wilder idea. Some physicists once imagined that maybe the universe doesn't really contain trillions of separate electrons and positrons. Maybe there is only one electron moving forward through time, then turning, going backward, then forward again, and when it's in its backward phase, we observe it as a positron. Whether or not that story is literally true doesn't matter much as the fact that it makes the math beautifully consistent. And in physics, the rule is simple. If a model predicts correctly and survives every test, it earns respect. Here's another strange truth. Most fundamental equations of physics don't actually care which way time is flowing. If you recorded the microscopic world and played it in reverse, the laws would still look valid. In everyday life, things clearly go one way. Broken cups don't reassemble, heat spreads out, and the future always feels unknown. But deep down, in the quantum world, symmetry allows particles to behave as if time can run both directions. The weirdest part is that even with our most precise atomic clocks and powerful equations, we still don't fully understand what time is. We experience it as motion, as flow, as a one-way river, but physics often treats it more like a dimension, similar to space. Antimatter might be hinting that there's something deeper about time that we simply haven't unlocked yet. Then come nothing. At the moment of the Big Bang, matter and antimatter should have been created in equal amounts. If that had happened perfectly, everything would have annihilated into pure energy. No stars, no planets, no life, no us. Yet here we are, in a universe filled with matter. That means something favored matter over antimatter, just slightly, but enough to shape everything. Some scientists suspect that the breaking of time symmetry may be connected to that imbalance. If that's true, then antimatter might not just be exotic science, it could be part of the reason the universe even exists. Here is one symmetry that has never failed in experiments: CPT symmetry, charge, parity, and time. If you flip a particle into its antimatter version, mirror its world, and reverse its direction of time, physics behaves exactly the same. In other words, an antiparticle moving backward in time in a mirrored universe would look identical to an ordinary particle moving forward in ours. It's dizzying, but it suggests that reality respects a kind of deep cosmic balance. So, does antimatter really move backward in time? The honest answer is that physics doesn't claim certainty, but the equations that treat it that way work beautifully, and they match what we see in experiments. Maybe particles don't literally feel time like we do. Maybe time isn't a straight arrow at all, but something more flexible and strange than human intuition can grasp. What we do know is that every time we study antimatter, it forces us to rethink what we thought was obvious and reminds us that the universe is far more mysterious than it first appears. And that mystery is exactly what makes science worth exploring. Why these rules? Why this interaction strength? Where the amplitude for probability? Why arrows at all? After a century, we still have no answers. The theory is spectacularly successful, but the deeper why remains out of reach. Science tells us how nature behaves with stunning accuracy, but ultimate why questions may have no answer, or the answer may just be that's how it is. The world we experience, solid objects, straight lines, definite events, is an emergent illusion. Beneath it, reality is paths upon paths, amplitudes interfering, probability fundamental. There's no hidden clockwork determining outcomes. Randomness is real. Many great physicists resisted this for decades. Experiments left no choice. Nature doesn't hide secrets here. This is the bottom layer. Yet from this strange foundation emerges everything: chemistry, biology, lasers, the beauty of the world. We're still exploring, still calculating, still searching for cracks or deeper truths. So far, none. Just this elegant, absurd, profoundly accurate picture of light exploring every path at once. And somehow, against all intuition, always getting the answer right.